love to act huge, but inside, a lot of their feed-forward neurons are basically chilling on the couch. This paper asks a fun question. What if we let most of them stay quiet and actually make that save real GPU work? The trick is not just sparsity. Sparse models have been around forever. The trick is making modern GPUs stop grumbling about irregular sparse data. So the authors build a new sparse format called TwELL for inference, plus a hybrid format for training, and wrap them in custom CUDA kernels. The result is a language model that keeps similar quality, but moves faster, uses less memory, and burns less energy. Same transformer vibes, fewer busy neurons, less GPU drama.
We all know that LLMs have completely transformed how we handle text, but they come with a massive price tag in terms of computing power. If we want to keep scaling these models, we have to find ways to make them more efficient. One of the most promising paths is sparsity. Essentially, just ignoring the parts of the model that aren't doing much heavy lifting. The authors focus specifically on the feed-forward layers, which are the real resource hogs here. They've introduced a new way to pack sparse data and custom kernels for GPUs to ensure that this sparsity actually translates into real-world speed. If you look at Figure 1, you can see how they do this by comparing their new format, called tile-wise LPAC, or TwELL, against a standard baseline. While the baseline stores data in a rigid, padded structure, this new approach uses a tiled format. By breaking the data into smaller, manageable chunks, they can track non-zero values much more efficiently. It's not just about saving memory. It's about making sure the hardware can process these sparse structures without breaking a sweat. The core issue we're facing is a frustrating paradox. Even though sparse models theoretically require less computation, they often run slower than dense ones on modern hardware. This happens because GPUs are built for dense, predictable math, and managing the bookkeeping for sparse data, like tracking where the non-zero values are, creates overhead that kills performance. Previous attempts to fix this often required changing how models are trained, which makes them hard to adopt in the real world. To solve this, the authors introduce new kernels specifically designed for modern hardware using the TwELL format we just mentioned. This format is clever because it can be created right at the end of a matrix multiplication, which removes a major bottleneck that slowed down older methods. By fusing these operations into a single, optimized pipeline, they can actually realize the speed and memory benefits of sparsity. They show that with just a bit of simple regularization, you can make models extremely sparse without hurting their performance, leading to significant speedups in both training and inference. To understand how we make these models sparse, we first need to look at how they actually work. A gated feed-forward block takes an input and processes it through two parallel paths, one for the gate and one for the up projection. These are combined to create a hidden representation, which is then projected back down to the output size. You can think of this as a dynamic key-value memory system, where the model retrieves specific information based on the input. To force the model to become sparse, the authors use a very straightforward trick. They add an L1 penalty to the training process. This is essentially a mathematical tax on the activations. By calculating the average absolute value of these activations across all layers, and penalizing anything that isn't zero, the model learns to shut down unnecessary neurons. It's a simple, elegant way to induce sparsity without needing to overhaul the entire architecture. Now let's move from this training strategy to the actual hardware implementation, where they use custom kernels to ensure this sparse behavior translates into faster performance. To make sparse models run fast, we have to rethink how we store and process data. The traditional way, called LPAC, stores sparse data in a padded format that's easy to read but inefficient for modern hardware. The authors explain that while this works for simple tasks, it creates a bottleneck when you try to use it in a complex, gated feed-forward block. The solution is their TwELL format, which is designed for kernel fusion. Instead of treating the sparse data as a separate, static object, they integrate the packing process directly into the computation. Take a look at algorithm 1. It shows how they scan through tiles of data, picking out only the non-zero values and packing them into a compact structure as they go. Then, Algorithm 2 takes this packed data and performs the necessary projections in one go. By fusing these steps, they avoid the expensive synchronization that usually happens when you try to switch between dense and sparse operations. It's a clever way to keep the GPU busy with actual math rather than wasting time shuffling data around. To make these models truly fast, the authors move beyond just storing data differently. They change how the GPU actually calculates the results. Instead of decompressing sparse data, they use a fused kernel that performs the math directly on the packed format. Equation 3 is the heart of this process. It shows how the kernel loops through the tiles of data, grabbing only the non-zero values and their indices to perform the necessary multiplications. By keeping the data in this packed state, the kernel avoids the massive overhead of moving data in and out of the GPU's main memory. It's like having a specialized assembly line, where you only pick up the parts you need, rather than moving the entire warehouse. The kernel is designed to be highly parallel, with different parts of the GPU working on different rows of the input simultaneously. This approach maximizes the use of the GPU's high-speed cache, ensuring that the computation stays fast even as the model scales up. Training large models is a memory nightmare, because you have to store all those intermediate activations for backpropagation. The authors tackle this by introducing a hybrid sparse format. Instead of forcing every row into a rigid sparse structure, they dynamically split rows. Most go into a compact sparse format, while a few dense rows are kept as backups. This handles the non-uniformity of sparsity across different tokens, which is a huge problem in real-world training. Next, they build custom kernels to handle this hybrid data during both the forward and backward passes. The key insight here is that they can perform backpropagation entirely within this sparse framework. Equation 4 shows the math behind this, illustrating how they calculate gradients for weights and inputs using the stored sparse patterns. By avoiding dense computation during the backward pass, they drastically reduce memory usage. It's a clever way to keep the training pipeline lean, ensuring that the speed gains they achieved for inference also apply to the much more demanding task of training the model from scratch. Now we're getting into the experimental side of things. Figure 2 is a great visual for understanding the trade-off between sparsity and performance. It shows that as you crank up the L1 regularization, the training loss increases, but only slightly. This confirms that you can force the model to be sparse without ruining its ability to learn. It's a balancing act, but the curves show that the impact is quite manageable. Next, look at algorithm 3, which shows how they actually handle this hybrid data during training. Because the model isn't uniformly sparse, they need a way to process both the sparse rows and the dense backup rows in the same pipeline. The algorithm essentially acts as a traffic controller, looking at each row and deciding whether to use the fast, sparse path or the standard, dense path. By doing this in parallel, they keep the GPU fully utilized. It's a smart way to handle the messy reality of real-world data. The experimental results really drive home the point that sparsity is a practical tool. Figure 3 shows that you can push a model to be incredibly sparse, where only a tiny fraction of neurons are active, without seeing a major drop in performance. It's a balancing act, but the data suggests that the model is surprisingly resilient. If you look at figures 4 and 5, you can see the real-world payoff. For inference, you're looking at over 30% speedups and energy savings as you increase the sparsity. For training, the memory reduction is particularly impressive. By using their hybrid kernels, the authors show that they can cut down on memory usage while simultaneously speeding up the training steps. It's not just a theoretical win. These charts demonstrate that the approach works across the board, making models faster, lighter, and more energy efficient. The takeaway is clear: you don't need to keep every single neuron active to maintain high performance. Table 1 is the highlight of the paper, because it shows that you can have your cake and eat it too. It compares dense models against the authors, sparse versions across various sizes, and the results are striking. Across the board, the sparse models maintain almost identical accuracy to the dense ones, which is the most important part. You aren't losing performance, but look at the efficiency gains. You're seeing double-digit percentage improvements in inference speed and energy savings. Even more impressive is the training side, where the sparse models show faster throughput and significantly lower peak memory usage. The authors point out that as models get larger, these benefits actually grow, which is a huge deal for scaling. They suggest that sparsity isn't just a niche trick, it's a fundamental way to make future models more sustainable. By showing that these gains hold up from small models all the way to 2 billion parameter ones, they make a very strong case that sparsity should be a standard part of how we build and train LLMs moving forward. This final section is fascinating because it shows that LLMs aren't just black boxes. They have a clear, interpretable structure in how they use their neurons. Figure 6 shows that the model is smart about where it spends its energy. The early layers are quiet. The middle layers do the heavy lifting, and the later layers are consistently sparse. The authors found a near-perfect inverse correlation between how sparse a layer is and how much speed up they get, which confirms their kernel design is working exactly as intended. Finally, Figure 7 digs into the why behind this sparsity. It turns out the model is highly selective about which tokens it pays attention to. Common, predictable words like the or simple web links barely trigger any neurons, while important, content-heavy words like specific nouns or verbs light up the network. Even more interesting is the position-based activity. The model dumps most of its computational power into the very first tokens of a sequence to set the stage. This isn't just efficient, it's a window into how these models actually process information. Thanks for joining us today. Happy exploring together.